Scanpath basically means how your eyes move when you're looking at something. It shows how your attention changes over time. What we've done in this work is create a deep Markov model that can predict scan paths for 360-degree images. The model uses the hidden state called Z to represent attentional landscape, and then produces coordinate of gaze point, which we call x tilde. Here we introduce some new designs. First, we propose a practical strategy for the visual state initialization. It helps start the model off on the right foot, which in turn lets us assign a specific starting point for scan path generation. Second, we introduce a semantic guided transition function. Basically, this means that we've created a way for the model to maintaining and updating memory. Our model is highly accurate and efficient for real-world applications. We also show two applications to show its generalizability. Let's talk a bit about scan paths in 360-degree images. 360-degree images are greatly different from 2D images because they offer a much larger space to explore. But at the same time, users can only see a small part of the scene at any given moment, which is different from 2D visuals where you can see everything at once. Also, the scan paths in 360-degree images can look like they jump around when you project them onto a 2D plane, because the left and right edges of the image are actually connected. Because users can only see a limited part of the scene at any given time, the starting point of their viewing has a big impact on their scan paths. In fact, even if they only look for a short time, starting from a different point can lead to a completely different viewing experience. There are two main types of methods for predicting scan paths in 360-degree images: saliency-based and generative. Saliency-based methods use a map to guess where people will look, but they don't account for how people move their eyes over time. Generative methods use advanced models like generative adversarial networks to predict realistic scan paths, but they don't always pay attention to the important parts of the image. The problem is, none of these methods really take into neither time dependency of viewing behavior, nor viewing conditions, like starting from a different point. This is important if we want to model how people actually look at in 360-degree scenes. To address these issues, we propose a deep Markov model, named ScanDMM. Recalling that in our model, we represent the visual state at a certain time as ZT, which is modeled using a Gaussian function with n dimensions. The produced coordinate of gaze point is denoted as x tilde t, which is a 3D coordinate. We also have an encoded representation of the scene semantics, represented as s hat. In the next, we will explain how our model predicts scan paths. To start the scan path prediction, we initialize the visual state Z0 in a simple but effective way. We directly use the starting point, x1, as input to a set of linear neural networks to learn the representation of the initial visual state. This way, we actually have a launcher for scan path prediction, which helps our model to focus on learning the dynamics of states more effectively, rather than starting from scratch randomly. This is important because the Markov model works like a chain reaction. To move from one visual state to the next, we use a semantic guided transition function. We first extract the scene semantics of a 360-degree image using a spherical convolutional network. The semantic feature provides important information about the scene to guide gaze behaviors. During the state transition, the scene semantic feature consistently influences the nonlinear dynamics of the states. This is done using an adaptive uncertainty weighting function, which works like the gate function of a long-short memory network. It determines how much of the previous visual state components need to be updated. Emission function describes how a gaze point is generated from the visual state. We first map the state, Z, into three-dimensional Gaussian densities, then model the emission process by sampling x tilde from the three-dimensional Gaussian densities. This is the overall framework of our method. To sum up, our method can reserve the spherical characteristics of 360-degree images by extracting the scene semantics on spherical domain and representing the scan paths using three-dimensional coordinates. We model the time dependency of gaze behaviors in a natural way by learning the nonlinear dynamics of the states in Markov chain. Our model is also flexible because the scan paths can be generated from arbitrary starting points and to arbitrary lengths. We present some qualitative results of our method, compared with other advanced methods. In the 4 scenes provided, we can observe that the predicted scan paths of our method, as shown in the last column, are more realistic than the others. Here are some quantitative results. We have conducted experiments on 4 publicly available databases and used 3 common metrics to evaluate the performance of the models. We can observe that our model outperforms the competing models in the most cases. In terms of efficiency, our model has the smallest size and runs faster than competing models. Our model can generate 1000 scan paths for a 360-degree image within 1 second, which is critical for real-world applications. In our ablation study, we evaluate the contribution of the state initialization strategy and scene semantics to the final results of our model. The figure displays different predictions of the variance of our model. The upper row shows Scanpath samples, and the bottom row shows the saliency map produced by converging 1000 scan paths. We can observe that removing the state initialization strategy may cause the produced scan paths to be overly concentrated on salient items. Removing the scene semantics results in an attention-less model, which causes apparent bias. Finally, by removing both the state initialization strategy and scene semantics, we found that such a model can only learn the general pattern of viewing behaviors regardless of the image content. In contrast, our final model can produce realistic scan paths. These results emphasize the significance of our learning strategies. We applied our model to 2 other computer vision tasks, one of which is saliency detection. We first generate 1000 scan paths and then convert these results to compute the saliency map. From the figure, we can observe that our model can obtain results close to the ground truth. The quantitative results also show promising performance of our model, and we even outperform the models specifically tailored for saliency detection. Another task is visual quality assessment. In this application, we use a specific computation framework for quality assessment of 360-degree images, where the scan paths are used for extracting viewport sequence. The experimental results show that the performances of different quality measurements are similar when using the scan paths produced by our model and using human scan paths. This proves that our model can produce realistic scan paths that are close to human scan paths. In this study, we introduce a deep Markov model for Scanpath prediction of 360-degree images, which is the first to model the time-dependent viewing behaviors in 360-degree scene. Our model is accuracy, flexible, fast, and generalizable, which is critical for real-world applications. Thanks much for your attention.